Okay, I think we are good on that camera. So we are picking up today with lesson 6.4. So this is lesson 6.4 in your textbook. And just a reminder, if you'll remember from the little quiz we did, you should be writing everything I've written on the board. Everything that's on the board should make it into your notes. And a little bit later, I'm going to make some more room over here for an example we're going to do on the graph. So everything that's on the graph and everything that is currently written or will ever be written on the board, you should have in your notes, as well as the things you see here in the bottom left-hand side of the screen. So a reminder that your notes should include the objectives for the lesson, which are under, it says lesson 6.4, and then there's those questions. Those are our objectives for the lesson to answer those questions. And then the recall, which again is like previously on your math education. Those are points that you're remembering from your previous, that you've learned before, maybe even just in the last lesson. Okay? So just to introduce what we're talking about, we're going to be talking about translating linear functions. And that means moving them around on a graph. Okay? So how can we manipulate linear equations and what does it do to their shape? And we're going to introduce how to do this by talking about something called families of functions. So the first question we're going to try to answer is, what is a family of functions? Right? And that will lead into what is a parameter of a function. And then we'll try to answer, how can parameters help us to interpret functions? So how can looking at the parameters of a function help us to interpret different functions? Okay? So that's our objectives for this lesson. And then just some things you'll want to remember that you've learned before that will be helpful in this lesson. One is that slope-intercept form of a linear equation is y equals mx plus b. And again, that's over here in the bottom left-hand corner. Y equals mx plus b, where m equals slope and b equals y-intercept. All right, so just recall that that's a form of a linear equation. We learned that in the last lesson. Also, functions can be used to model real-world situations. So the x's and y's of linear equations can be mapped to real-world sets of data to model actual situations. So that's something else you want to remember when we start to look at why it's important to understand families of functions and parameters of functions. All right, so let's go ahead and get underway. I'll make sure we're still recording because sometimes we've had trouble with that. And yep, looks like we are still good. So right here, I'm going to start off by just telling you straight away, a family of functions is a set of functions which all have a set of characteristics in common. So remember, a function is a relationship with an input, with a set of inputs and a set of outputs, where every input maps to exactly one output. And I'm doing this because it's x's and y's, so a horizontal characteristic and a vertical characteristic on the graph. And so if you took a bunch of those, right, maybe it's a line like this, and a line like this, and a line like this, and if they all share a common set of characteristics, we can call them a family of functions. All right, so for example, here are some functions that we haven't really dealt with yet, but I'm going to use them to illustrate what I'm talking about. Okay, so and then we'll talk about how it applies to linear functions, which is what we have dealt with and what we're dealing with today. All right, but I want you to kind of just sketch these in your notes as just an illustration of what we're talking about. So, for instance, right here I have graphed the function f of x equals the absolute value of x. F of x equals the absolute value of x. And it looks like a nice little V here, where each of these lines, or rays, I guess they would be called, are at 45 degrees. Okay? And but then there are other functions that are in the same family, so they have the same form, that are f of x equals 5 times the absolute value of x, or f of x equals the absolute value of the quantity x plus 7. Right, so each of these would look a little different. This one would actually be like a vertical stretch, so we get narrower. Okay. This one would be a horizontal slide, so it would actually slide 7 units to the left. The overall shape would stay the same, but it would slide this way. So we can take this function and move it around, or squeeze it like this. Okay. But those are all going to be in the same family. All right, so similarly, here is f of x equals x squared, just a basic sketch, and maybe something you've seen before. And again, these are functions that would be in the same family. So if you just take this function and multiply by 3, so f of x equals 3x squared, again, it would start to stretch it like this, so it would get skinnier, but they're in the same family. They share some common characteristics based around this x squared. You could also do f of x equals x squared minus 12, which actually would take this and move it down. So the same shape, it would be further down. Okay? So those would all be in the same family. All right? So let's look at the f of x equals x is kind of a base linear function. So this is something you're familiar with. The graph looks like this. It's a line at 45 degrees through the origin. Right? So f of x equals x, linear functions are a family of functions. These functions that I have graphed are called parent over right and left, okay? But this f of x equals x, that's at 45 degrees through the origin, is the parent linear function. So that's what this says right here. Or, no, you don't have to write that down. But f of x, linear functions are a family of functions with this function as their parent, okay? So the parent linear function could be written like this: y equals 1x plus 0. Okay? So we have slope of 1 and y-intercept of 0. So the slope is 1, and it crosses the y-axis at 0. Okay? So that's the parent linear function. Right? Now, to understand how we can manipulate functions within a family or to create the child functions, okay? For y equals mx plus b, all right, so this is that slope-intercept form we remembered earlier. Slope and y-intercept are called parameters, all right? So how do we get from a parent to a child? We manipulate our parameters, all right? And so in this case, we either change the slope or change the y-intercept. And that will give us something that's sort of like the parent. It's a linear function, but it's different in that it has a different slope or a different y-intercept, okay? So when we're dealing with y equals mx plus b, which is sort of one of our favorite forms of linear functions because we can pull out the information we need so easily, okay? When we're dealing with y equals mx plus b, slope and y-intercept, slope m and y-intercept b are our parameters. The parameters are the numbers in the equation that determine the shape of the child function. And I put shape and child in parentheses because I'm sort of making up those words to describe to you what we're talking about. Okay? So again, if at 45 degrees through the origin is our parent function, we can change the slope, which will, where's my scepter? We can change the slope, okay, which will move it like this, or like this, or we can change the position, okay, which moves it up and down. We could also change the slope and the position, right? The slope and the position. All right, so those two things are parameters that determine what I'm calling the shape, right? Which is kind of like how it's tilted or where it's positioned, how it looks. The parameters determine how the child function looks. All right, so you might have y equals 5x plus 7. Y equals 1/2 x minus 30. Right? It's going to change the way the function is positioned. And that's what we've been doing through the last couple of lessons, is looking at different functions and graphing them and seeing how they look different. And so now we're introducing the concept that these parameters are the numbers in the equation that determine what the function looks like as a graph. All right, so what does this mean? How does this actually help us to interpret some graphs, some functions, right? How can we use this? Well, there's an example in your book on page 272, okay? There's an example in your book on page 272 that talks about a gym membership, like a workout gym, right? Where you go to get fit, or swole, as it were, right? So it's a gym, and their current setup, all right, of $50. $50 startup fee, after you've paid the initial, how much it costs to be, all right, of t plus 50. Okay? So notice, you start with the $50 fee, and you add $25 for every month. So if you've been a member for 2 months, it's $50 startup fee plus 25 times 2 is another $50, $100 to have been a member for 2 months. Okay? So, and note that the new member fee is in the place of the y-intercept. Because when time is 0, when no time has passed, when I have not been a member for any months, 0 months, I've already paid $50. So the y-intercept is 50 because when x, the input, time, is 0, the cost, y, is still 50. So 50 is the new member fee is the y-intercept. And 25 is the slope, because the rate of change of the cost for me goes up $25 every time the time goes up 1 month. Okay? So it's 25 over 1. The change in y, the change in cost, over the change in time is $25 per 1 month. So the slope is 25. Okay? So notice that these are our b and our m, our y-intercept and our slope. And so here's a graph of what the cost of being a member of this gym looks like. My scale here is, my y scale is 25 for every line. Each one of these lines represents $25. Okay? And each one of these lines represents 1 month. Okay? So notice, I started right here, 2 lines up, because I'm starting at $50. Every month I go over 1, I go up another $25. Right? So y-intercept of 50, slope of 25 over 1. Okay? So the parameters of this is in the family of linear functions, and the parameters are y-intercept of 50 and a slope of 25. So now the question is, what happens if you decrease the new member fee to $0? So a lot of gyms, after the first of the year, people are making New Year's resolutions where they want to get back in the gym. So the workout gyms say, here's what we'll do. We'll make it really easy for you to sign up. We'll say no new member fee. $0 new member fee. Okay? So special. New member fee equals $0. Right? So they're running a special. So now our C of t becomes 25t plus 0. So the cost at time 0 has gone from $50 to $0. Okay? So let's see what that looks like on our graph. So now our y-intercept is 0, so it's going to start right here. But our slope, 25, is still the same. So we're still going to go, again, my scale is 25 for every line on the y and 1 month for every line on the x. So I'm going to go right here, right here, right here, right here. Okay? So I started at y-intercept 0, and I maintained the slope of 25 over 1. So that gives me an amended function that looks like this. Okay? It's a little bit off, but close. So notice the slope stayed the same, right? 25, 25. And so the tilt of these lines is the same. We didn't change the slope, so it's about like this. All we did was slide it down. So this is called a transformation. When we move a function or change its shape or slope, okay? So in this case, all we did was slide it down. Because we changed the y-intercept from 50 to 0, it maintains the same slope, it just went down by 50. Okay? So now let's say that the new year has passed, we're getting into the summer, and they're actually at capacity. Things are getting more competitive, right? So they've now since returned to having a $50 new member fee, okay? So that's still in place. But they said, you know what, we're not making enough money. We want to make more money on a month-to-month basis. So we're going to change our monthly fee from $25 to $75. Okay, we're going to change our monthly fee from $25 to $75. So now, right, sad face, rate increase. Now the monthly fee equals $75. Okay? So my new function is C of t equals 75t plus 50. Okay? 75t plus 50. So we now have changed the slope. The rate of change of the cost has gone up. Because now for every month, every change in x of 1, my change in y goes up not by 25 but by 75. So my slope is now change in y 75 over change in x 1. Okay? My rise over run or however you want to describe your slope, the slope has changed because the rate of change of the cost has changed. Okay? So now we still start at 50. Our y-intercept is 50, so that's right here still. But now my slope is not 25 over 1, it's 75 over 1. So I'm going to go up 25, 50, 75 over 1, up 25, 50, 75 over 1, up 25, 50, 75 over 1. Okay? So now, we didn't change the vertical position of the line. Okay? If you can't see it, it's right here. Okay? The original is right here. The new one is right here. Okay? So, but what we did was we changed the slope. Okay? It got steeper. The cost of being a member goes up faster because we changed the monthly fee. The monthly fee got higher, so I am paying more quicker, right? So the slope went from this to this. But the y-intercept stayed the same because the cost at time 0 is still 50, okay? So the cost at time 0 is still 50, the y-intercept is still 50, but each month I'm paying more than I was in the original situation, so my slope has gone higher. The slope is steeper. Okay? So that is families of functions and translations. So what we start with a parent function, and by applying translations, by changing some parameters, we get child functions. We get functions that look slightly different but share some characteristics. Okay, so that is what we're going to be talking about when we reconvene in our next class. We'll be doing some exercises around these. So make sure you've gotten all the notes down. And then when we reconvene, I'll do a couple of examples from the exercises, and then I'll release you to knock it out. All right, so I will see you next time.